Causal policy gradient for whole body MoMa manipulation. In recent years, we have seen huge success in applying reinforcement learning algorithms to solve navigation and stationary manipulation tasks in robotics based only on sensor data. However, combining these successes to learn policies for whole body motions in mobile manipulation is difficult. An important reason for this difficulty is the large action space of the mobile manipulator, combining degrees of freedom of the base, the arm, the gripper, and the head, and a complex reward function often composed of multiple reward terms representing multiple sub-objectives, like reaching a location with the end effector while avoiding collision, not dropping a carried object, and keeping a target goal in the field of view of the head camera. When reinforcement learning algorithms are applied to solve mobile manipulation tasks, the policy is typically updated using the sum of the reward terms. Such an update process implicitly assumes that all dimensions of the action space plays a role on all of the reward terms that the agent can obtain. In these conditions, common policy learning algorithms fail due to the large variance in the policy gradient computation, resulting in unstable training. However, mobile manipulation tasks can often contain special structure, where each action dimension can only affect a subset of the reward term. Our key insight is that by removing redundant action reward connectivities, we can reduce policy gradient variance and obtain a more stable RL training for mobile manipulation tasks. In this work, we propose Causal MoMa, a two-step procedure to train RL policies for mobile manipulation tasks. In the first step, Causal MoMa identifies the causal dependencies between action dimensions and reward terms through estimating their conditional mutual information and encodes them in a binary causal matrix. In the second step, Causal MoMa exploits this structure in a causal policy gradient implementation that reduces gradient variance by taking into account only related reward terms to update action dimensions. We first evaluate Causal MoMa in simulation domains, including a mini-grid simulation environment that requires virtual arm actions to succeed, and an iGibson simulation environment where we test with two different realistic robot models, Fetch and HSR. In all domains, Causal MoMa trains successfully, improving over baselines. Next, we test in a real-world environment where we evaluate zero-shot transferring the best policy trained in simulation to a physical HSR robot. In this experiment, we test in an apartment scene never seen by the robot during training. The policy trained with Causal MoMa generalizes well to this completely unseen domain, improving over a planning-based solution with access to the layout of the environment. Although our policy is not training on dynamic goal or obstacle, the policy can react to dynamic goal and obstacle robustly. By comparison, the whole body RRT planner that we compare against struggles against dynamic goals and obstacles. As a result, Causal MoMa is able to obtain a significantly superior performance in the dynamic scenario. The reactive nature of our policy allows it to deal with emerging constraints and act accordingly, as shown in this clip, where the robot reapproaches the goal from a different angle when an obstacle appears. Our policy is also capable of completing semantically meaningful tasks. In this clip, we're showing the robot following a human. In the bottom right, we show the robot's head camera's view. Notice how the robot is always trying to keep the target within its field of view while dynamically adjusting its arm post based on its distance with the target. Finally, we show a relatively complex task of the robot carrying a cup of beads without spilling any, and eventually pouring them into a bowl, avoiding obstacles in the process.